Okay, guys, so in this second lab, we will discuss quality assessment of ranking systems. Also, you have you have the second homework that will be released. And this second homework will be implementing all those metrics with which we can assess the quality of a ranking system. So basically, when we are building a system, we need to find a way to measure and assess the performances of the system. You know, in the classical machine learning, you have metrics as accuracy, precision, recall, right? And those metrics are based on the true positive or false positive of the prediction, if you're talking about classification. But for ranking, it's a bit different because when you're talking about ranking, you also care about the position of item being ranked. Okay, so if you rank item at the bottom of the search engine, or you does not return even like relevant item to a search query, okay, this means that your ranking is not that good. It's not even good. So we will assess the performances of a ranking system by the ability to return relevant document, okay, and also the ability to rank those relevant documents in the top of the rankings, okay? If you search, for example, I'm looking for pancakes on a search engine, okay? You expect to see the pancakes as first result, okay? And in most of the time, you don't even open the second page, okay? So if you are then building a ranking system, how can you then compare if this model of this ranker is better than the other ranker? So we need to come out with new metrics that will also account for the position of the items being ranked, okay? So that's why we have several metrics that will account for those positions, okay? I will share my screen and we will go through the whiteboard exercise that you had in the lecture. I'm not sure you did it. So we try to compute each metric in different cases and see why are they designed like that and how you need to implement them in practice. So I will share the whiteboard. There's something in the waiting room. Let me see. Okay. Okay. Well. So I hope you can see my screen. I don't know if I can move this. Okay, nice. So in this example, you have a set of relevant documents, okay? And you have a set of queries. For each queries, you have the ranking, okay? And so you have two queries. You have query 1, query 2, and you have the corresponding ranking that has been provided by the ranker that we want to assess the performances, right? And here we want to measure the mean average precision. So this ranking return the first document. This is relevant, 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 and in between we have irrelevant documents, okay? And the mean average precision uses the precision as base matrix, okay? So can you recall the formula of the precision, or what is the precision? So you have the precision here. Is the amount of true positive divided by plus false positive. Why? Because if you take the case of, let's say we want to predict if someone have the cancer or no, okay? The precision is how good is our system when it comes to predict if someone has the cancer or no, like the precision. Among the predicted positive, how many are actually positive, okay? This means among the retrieved document, how many are actually relevant, okay? But when it comes to recall, is the inverse. We think of among the positive one, okay? How many has been predicted as positive? It's a bit like the inverse. So for the recall, we will look at the true positive divided by the true positive plus the false negative should be. Yeah, false negative should be. So you have this difference. So for the average precision, we will use those notion. But just here, the precision is different from the precision that you see in the ranking, in the classification, for example. Okay. So here we pay attention of the precision at the time that we retrieve the document. Okay. When I take the document, I compute the precision. At this particular moment, what is the precision? Okay. But the recall will be the recall among all the relevant documents. So when I think about the recall, I say, okay, I have 10 relevant documents. At this time of the retrieval, how many of them has been retrieved, okay? But for the precision, we just take as among the retrieved document, how many are actually relevant? Does that make sense? What does it mean? Okay, so guess, can you state your name or tell us you're not a spy? If you cannot write your name properly, we will kick you out, yes. Okay. So let's compute the precision at each time. So when we are at this level, what is the precision after retrieving this document? What is the precision? Yeah, the precision is 1. Because among the document that I retrieve, it's exactly a relevant document. What about the recall? The recall will be among the retrieved, among the relevant documents, how many relevant did I return? Yeah, 1/5, because I have 5 relevant documents and I retrieved 1 from them. Next, retrieve irrelevant document. As this document is irrelevant, the precision will decrease. Okay, so we have here 2 divided by 1 divided by 2. Okay, next, what about the recall? The recall remains the same. Okay, because from my 5 document, I just retrieved 1. And the precision again here, I retrieve 1 more relevant document, okay, among 3 retrieved documents, okay? And the recall will be 2 of, no, the recall, yeah, increases as well, 2/5. And next, we have 2/4, because this is not relevant, okay? And here we have 3/5, not relevant. The document is relevant. I wrote 3. This should be 2. Yeah. The document is relevant, so we have 3 relevant document retrieved out of 6. How is the recall? Here the recall remained unchanged because there's no relevant document retrieved, right? But here there's 1 more relevant document retrieved, so we have 4/5.
3.
Yeah, 3. Thanks. So we have 3/5. And next we have another irrelevant document. So this remains 3/7 now. Okay, but here this does not change. And here next 3/8, and here 5. We retrieve another relevant document. So now we have 4 relevant documents out of 9 retrieved documents. And here we have 4 relevant documents out of 5 actually relevant documents. And finally, we have 5/10. And here we have 5/5. Okay. For the second query, we compute the precision in the same manner. So first, the document is not relevant. Okay, so my precision is 0. Okay, what about my recall? Also 0, because among the relevant document, I return nothing. Okay. And next, the precision will pass to one document retrieved out of 2. And here we one document retrieved out of 3. And share 1 out of 3, 1 out of 4, share remain unchanged, and share 2 out of 5, share it also changes 2 out of 3. And next, 2 out of 6, and share the same. Yeah, here is remain the same. So 2 out of 3. Next. Yeah, 3 out of 7. Here, 3 out of 3. So here will be 3 out of 3, 3 out of 3, 3 out of 3. And here we have 3 out of 8, 3 out of 9, and 3 out of 10. Well, so and next we have the average precision. So mean average precision uses the average precision. The average precision just pay attention to when I retrieve a relevant document. Okay, because we want to be like tolerant to irrelevant documents. Okay, because sometimes we also introduce documents that are assumed irrelevant, but the user feedback can help us to update. Okay, but to measure the performances, we just pay attention to at which moment we ranked the relevant documents. Okay, so to compute the average precision, we just pay attention to every time that we return, we found a relevant document. What was the precision at that time? And that's what we average. Does that make sense? This means that for this case, yes?
I lost focus for one moment because you
yeah, I said like to compute the average precision, okay, we pay much attention to the moment when we retrieve relevant documents.
And
which is when you found like relevant document share, relevant document share, relevant document share, relevant document share. We do not pay attention to this one. But this will help us to give like lowest value to the precision when we retrieve a relevant document at the end. For example, does that make sense? Because let's sum up everything to have the average precision. We will get the intuition. So we have one relevant document that has been retrieved at this time, another share, and the precision was this one. Okay, and share, and share, and share. So we have 1 plus 2 over 3 plus 2 over
3 over 6.
Yeah, 3 over 6 plus 4 over 9 plus 5 over 10. And then we average this. Divide by 5. Okay? We do the same for the second query. These are the relevant document that we retrieve and the precision at that time. We average that. So what will we get? 1/2 plus 2 over 5, yes, plus 3 over 7. Everything divided by 3. Okay? In the name, you have mean, average, precision. Okay? So we have the average precision, and then we complete the mean for all the average precision that we got. And those average precision are linked to every query. Okay? Let's just assume that we got another rank here that returned this kind of ranking. Let's be very fast. And for this ranker, we got relevant documents here. Okay. According to you, what will be the precision, the average precision? Will be exactly 1, right? Because you have 1, 1, 1, 1, 1. Okay. And then, yeah, this one is better. It's more precise because it ranked relevant document at the top of the list, okay? That's why we pay attention to the moment where we retrieve relevant document, okay? Because if you have others value there, it's not important for us. It's just important when we retrieve them, okay? But if there was another relevant document, but it has been returned somewhere here, okay? We can see that this will decrease the average precision. It will not be 1 anymore, okay? The same if you have another one there. Is it clear? So that is the intuition behind the average precision computation. Okay. So for the final response, you will take the average precision for the first query plus the average precision for the second query, okay? And then you average that, divide by 2, okay? So what you have here, what you get here and here, you plug it there to have the final value, okay? So if you have a ranker that we have average precision here 1, imagine the perfect ranker, okay? You have average precision here 1, average precision here 1, you have 1 plus 1 divided by 2, 1. It will give you the best value, okay? So something that will not follow this earlier ranking, we have a lower score. With this way, you can compare them 2 different rankers to say which one is better than the other, okay? You had this whiteboard time during the lecture, I guess you remember, where you are expected to have for, you have different queries. These are the queries, okay? These are the ranking for those queries, okay? Results that are in bold are the relevant one, okay? This means sure, this one is the relevant one, this is relevant, this is relevant, this is relevant, this is relevant, and the first and the last result are relevant, okay? So we want to compute the mean average precision for this ranker, okay? So first, what do we need? For every query, okay, we need to know what are the relevant documents, okay, to be able to compute the map. So, and then for each ranking, we will see where the relevant document has been placed, reaching the ranking, okay? So if we take the first ranking, which is this one, this is the first ranking. What is the relevant document? First position, so this is the relevant document. If we take the second rank, you see the third and fourth position. So we have third and fourth position, right? For the third rank, second and third, we have the relevance here. And for the last one, first and last. First and second, and last, okay. First and last. So now that I have this, I can compute the average precision, right? For each of these queries, for each of these rankings, okay? So for this one, the precision is 1, okay? Next position, it will be just 1 by 2, 1 by 3, 1 by 4, 1 by 5, okay? But what will be the average precision? It will be 1, because we pay much attention to when we return the relevant document, okay? If this relevant document were at the last position, it would have been 1 by 5, which is lower, okay? For the second document, we have irrelevant, irrelevant, 1 relevant, okay? Another one, another relevant, and share irrelevant. Yeah, 2 over 4, yeah, thanks. 2 over 4 and share 2 over 5, yeah. So for the average precision, we have 1, 3 plus 2, 4, everything divided by 2, okay? For the next document, we have here 1/2 and 2/3, right? And here we have, yes?
So we finally divided by the number of true ones, right?
Yes, we average between them. So because we have two
Because
relevant,
we have five like results and like 2 of them true. Maybe we should divide it by 5 or not.
no, you shouldn't divide by 5. Because we average the precisions that we have at the moment that we retrieve every document. Okay?
I see. But
this,
I mean, we have one last cell, for example, for the ranking 2.
yes.
We have three numbers which are involved into the averaging process, but we divide it by 2, right?
We divided which one by 2?
The sum of 1/3
Yeah,
and 2/4.
Yeah, we divided by 2 because we have only 2 relevant documents.
I see, thank you.
Yes, in this case, you can assume that we divided by 1. Okay?
Here, thank you.
Yeah, okay. So here you have precision 1, and the last position we have 2/5. And then the average precision will be 1 plus 2/5. Everything divided by 2, okay? And then to compute the map, the mean average precision, we take all the results that we have here. So here we have, let's say this is array 1, array 2, average 3, and average 4. You can compute it by your own to have the final value. And what we get like average 1 until average precision 4, everything that we divide by 4. Just take the mean, okay? Well, let's assume that our ranker is perfect. It knows how to rank perfectly each document. What will be the expected map value? It will be 1, okay? Because here the average will be 1. You have here 1, 1, 1, 1, okay? And you sum 1 divided by 4, have 1. You have a perfect ranker. Anything that shifts far away from this perfect ranker, we get like lower score. But something that on the rank everything will be close to 0 as the score, okay? Perfect. And then we have the discount cumulative gain, which is another metric that is used to measure or assess the performance of a ranking system. This one, similar to map, also account for the position of the relevant document in the ranking. So it divides the relevance by the logarithmic of the position. Okay, so what we do, we penalize when the document is relevant and it is placed at the end of the list or far away from the initial position, you get the score penalized because the logarithmic grows very slowly, okay? And we divide by very, okay, small numbers, okay?
Number of which is the same as before?
Yes. Yes, so we can compute the discount cumulative gain score using the same data set. Okay, yeah. So if you want to do it here, let's compute the discount cumulative gain for the first ranker here, okay? What will be the answer? We just have one relevant document. So you remember here, we extract the relevance of the first document and we add the rest because the restriction of the logarithmic there, okay? You cannot divide by 0. I mean, sure, we cannot divide by 0, okay? So the value will be exactly equal to 1 because the first document is the relevant document, okay? Thus, we just return the relevance of that particular document, okay? And then we compute the relevance of the second document. That will be what? What is the relevance of the first document in the ranking? We have the first document here. Is it relevant? No, it's not relevant, okay? So the relevance will be 0, okay? And plus, we check the relevance of the next document, which is also 0, but not only 0, but it will be logarithmic 3 of of 3, yes, of 0, plus now we found a relevant document, which is Google. So it will be 1 divided by logarithmic 2 of 4. Okay? You have the relevance there. Plus 1 divided by logarithmic 2 of 5, and plus 0 logarithmic 2 of 6. Okay? So you can see that this logarithmic will try to penalize relevant items that are being placed at the end. Okay? Just imagine that for this particular ranker, the relevant document were placed before. Okay? This will increase the score. Okay? If someone can compute these values and just tell us what is the answer. We want the answer of 1 divided by logarithmic base 2 of 4. Can you compute this, guys, and tell the answer? What is it equal to?
When somebody is computing, can I ask a question?
Yes, yes, do.
So what does DCG represent? I mean, just imagine we get some constant number in the end, and what does it represent? Is it better the higher or better the lower, or and what does it show in a query?
It shows you how good the ranking is. Okay, so the higher it is, the better it is as well. Okay, and we will see that we also normalize it. For this particular case, let's compute the discount cumulative gain for 2 different rankers. Okay, one that ranked the items at the beginning and another one that ranked them not at the beginning. You will see that the ranker that ranked the items at the beginning is having higher discount cumulative gain value. Okay. So if you are about to compare 2 different rankers with respect to DCJ, the one with the highest value will be the better. Okay.
We are comparing the performance of different queries, and this is some way to measure it.
Yeah.
How it works.
Yeah, exactly. It's the same as the accuracy. You have your classifier, you compute the accuracy, and you compare with another model. And you say that my model is more accurate. So for ranking, we do not use accuracy, but we use this kind of metrics.
Can you please scroll up to see the formula again?
Can I do what?
Yeah, that's fine. Just stay here.
Yeah, go ahead. What's the question?
Do we need to divide this by 4?
By?
By 4.
Why by 4?
Because this,
No. This is completely another metric. For this metric, you do not divide by 4, but we find that there is a normalized version. Okay.
E is the number of resulted queries, right? And
Yes.
what is rel?
What is what?
Rel.
It is the relevance of the document I. And if you check here, when the document is relevant, okay, the relevance is 1. What is irrelevant? Irrelevant is 0. Does that make sense?
Yeah. Thank you.
Do you have any value for that? So I will update the link when this meeting will end, okay? This is the free version. Yeah, I'll send you. Is there anyone computing that? If not, we can just move on. Because I want to show you something here. What is it important to normalize?
It is
0.993. Okay. Along with this, I hope you cannot see my screen sharing. Okay, I will have to stop sharing. Right. So along with this metric, there's something called the ideal DCG, because we want to normalize it. Okay, we normalize it by dividing with the ideal value. This means the value that we get if we use the perfect ranker. Okay, this means the ranker that rank everything at the beginning. So if you compute the ideal DCG for the query 2, for the ranking 2, this ideal ranker will rank these relevant documents. Where are they relevant? These two should be at the first and the second position, right? So we assume that for this particular case, we have 1 divided by log base 2 of exactly 1, because we have the relevance from the formula, we have the relevance before, okay? So we have 1 plus 1 divided by logarithmic base 2 of 3, okay? And the others will be 0 because they are irrelevant. All of this will be irrelevant, okay? So for this ideal, what is the value? It should be 1.6 something, okay? Yeah, it's 1.63. So this is the ideal one. Now we want to normalize. By normalizing, this means that you will compute the normalized discount cumulative gain of the query 2, okay? Which you divide this one by the ideal one. Does that make sense? So when you normalize, you will have what? 9.93 divided by 163. What is the value?
uh,
57. So you have 0.57. So imagine a ranker that rank everything at the beginning. When you normalize, what you will have? You have exactly 1. The perfect ranker, we have this score divided by the normalized factor, and you have 1 for that ranker. Okay? So the normalization tells you that the values will be between 0 and 1. Okay? The more closer is to, the more it is close to 1, the better your ranking system is. That makes sense? Yeah. So, and in the same way, you compute the ranking for this one, for this one. Okay? And you have the discount cumulative gains measure for that particular ranker. And then you have pFound. If you remember what you saw in the lecture about pFound, is that this metric kind of capture more than something more realistic, like what we have when we are searching. We are looking for through the result of a search engine. First, there's a probability that we will stop looking for further items because you didn't find what you were looking for, right? Yes, and the probability that you look at an item depends on the previous item, whether it was relevant or no. So if you find one result that is relevant, it is less likely that you will look at the next result, okay? So the probability that you look at the result will decrease. Okay, so here we will measure the performances based on those assumptions. Okay, and one thing is that the relevance is chosen like something to 0.4 recommended value based on statistic that has been studied, okay, in different ranking system, like on Google, for instance, okay? And also we assume that the probability that you will break, this means that you stop looking for further items, is equal to 0.15, okay? So these values are given, or they can be modified, yes? How can we? Sure. How can we do what? Find the value. This is the recommended value because this probability should be like, it has been measured empirically, for example, okay? Like to see, okay, we have different results, you go through the result, what is the probability that you stop looking further, okay? So this value is given, okay? It does not depend on the result that you have at the moment that you are measuring, okay? So one thing that you can notice is that the probability that you look at the first item is 1. Make sense? Because when you search for something, the probability that you will look at the first result is 1. You will definitely look at the first result, right? But the probability that you look at a given result is the probability that you looked at the previous result, okay? Multiply by 1 minus the probability of the relevance of that result, okay? So if the previous result were relevant, okay, this means that it decreases the probability that you will look at the next result. If it wasn't, it does not affect. You search for something, the first result is not interesting, you directly go to the next one, okay? But if the first is interesting, it is less likely that you will look at the next one, okay? And next, we also multiply the probability that you will stop searching, because you get fed up of searching because you didn't have like interesting result, and then you stop there, right? So based on this, we will compute the probability that we look at each result, okay? So here, what will be the probability that you look at the second item? It will be the probability that you looked the previous item, which is 1, right? Multiplied by 1 minus the relevance of the previous item. Was it relevant? No, it wasn't relevant, so it's 0, yes. And then we multiply by 1 minus 0.50, okay? What do we have here? Something like 1 multiplied by, yeah, 0.85. Next, the probability that you look at the third item is the probability that you look at the previous one, multiplied by 1 minus. The previous one was relevant, okay? We said that this probability will be 0.4, okay? Based on this assumption that we have, 0.4. Because it should also reduce it. If the previous was relevant, it's less likely that you look at the next one, okay? So we choose that probability to be 0.5 as well, okay? The probability of relevance, yes. Let me write it like this, P relevant. And then you also multiply this by 1 minus the probability that you will stop looking further, okay? What do we have here? We have 0. Multiplied by 0.6. Yeah, the first one we can just correct. Okay, guys, we have been interrupted. Let's continue. So when we compute the probability of looking here, it gives us something like 0.43, okay? And then the probability for looking at the fourth item will be 0.43. Divide by 1 minus 0.4, y minus 0.15. This will give us 0. This multiplied by 6 multiplied by 55. So here we have 0.22. And lastly, we have 0.22, the probability that we look at the previous item minus, was this item relevant? The previous item, the item 4, wasn't relevant. So here we have 0. And then we have 1 minus this. This gave us 0.22 by 0.8. Okay. 19. So what you can see is that the probability that you look at an item decreases when it goes down through the list. Okay. This means that this is also because the probability that you break, you stop looking for items. Now the pFound is computed as the probability that you look at an item, okay, multiplied by the probability of the relevance of that item. If you check here, okay, we sum everything up. So what do we have? Next, we will have 1 multiplied by the relevance of that item, probability of relevance. What's the probability of relevance? For that item is 0. It wasn't relevant at all. Then we continue 0.85 multiplied by 0.4 plus 0.83 multiplied by 0.4 plus 0 plus 0, okay? There wasn't relevant. So you can see that even though we give the probability of looking at the first item as 1, when we compute the pFound value, it cancels out because the item wasn't relevant. And we will sum up only for items that were relevant. And you can see it also accounts for the position, right? Because if this item were here, we have had 1 multiplied by 0.4. It should be higher, okay? The same for this item. So if we move them at the first position, we have a better value of pFound. Does that make sense? So you can see that all the metrics that we are using account for the positions somehow in a different way, but they are giving a different way of measuring performances. So someone may say, my ranker is better in terms of this metric, okay? Or is better in terms of all the metrics. So even if you're doing like research in information retrieval, okay, you will find all these metrics. These are the metrics that I use to compare approaches, compare method, compare algorithms, okay? Well, so I hope this was clear for all of you. We will then switch to the homework assignment and then discuss if there are some points that are not clear for you to highlight them. Which notebook? This note. Yeah, I will share it. Yeah, sure. So for the first exercise, you have to implement the mean average precision function. So make sure that you read the text that is there to understand everything. And in this function, you have to implement it, okay? But something that I want to emphasize here is the meaning of this input that you expect from the function that we compute, okay? So you have the test relevance and you have the test results. So assume that each vector here is the response of a query, okay? And each value inside corresponds to the ID of the document, okay? And then for this particular response, you have the document that are relevant reaching this ranking, okay? So this tells us that the document 9 is relevant, okay? The document 1 is also relevant, and the document 8 is also relevant. Okay, but next to it, you can see others value. This is assumed to be the relevant score, like which one is more relevant than other. But for the mean average precision, it assumes that the relevant is just Boolean, relevant or not relevant, okay? So you will not be using these values as they are just binary. They should be binary. But in other case, we'll also consider the case that document relevance is not just binary, but there's a relevance score, okay? Which can be greater. Like in some cases, we can assume that document 1 is relevant than document 2, which is relevant than document 3, okay? So some metrics will also account for that. For example, the discount cumulative gain, okay? But for this case, you just assume that they are binary, relevant or not relevant. And inside the function, we then implement the mean average precision. So for each query, you compute the average precision, you compute the average precision, compute the average precision, and then you average all of them to have the mean average precision. Is it clear? Well, and then you have the 11-point interpolated average. Let me get back if we can discuss also this for a few minutes. So we have this 11 points interpolation. Average. So for each recall, okay, you have the interpolated. You have the interpolated precision. Okay, why? If you check, I don't have it here. I have to switch again. If you check here, you can see that sometimes it is down, up, down, up, down, up, right? So if you want to exactly plot the mean average precision that we saw before, I'll have to stop and try again to fix this. So if we check the precision recall curve, where we have the precision, here we have the recall, right? If we check from what we did in the map, okay, you will see that sometimes the precision drops, goes up. You can see here, for example, here, it drops, okay, it goes up, okay, it drops again, it drops further, goes up, drop, drop, goes up, right? What about the average, the recall? The recall constant, go up, constant, okay? Go up, constant, go up, okay? So if you plot them, you will have a kind of, you have this kind of stuff where you have this goes down, go up, goes down, go up, okay? You have something like this, right? But for the 11 points interpolation, we just pay attention to the moment where the precision was high. Like we pay attention to the moment where the precision was high. So we check this and then we stop here, okay? And then we go here and then we stop here, okay? And so on and so on. So, and then we try to have something smoother that we can easily examine, okay? So why do we call it 11 points? Because we will have to define the threshold for the recall. So for a given recall, what is the maximum precision that we have, given that this is the minimum value of the recall? Let me make it clear. So we have 0, 0.1, 0.2, 0.3, 0.4, 0.9, and 1. These are the 11 points, okay? So here we assume that this is the minimum recall that we have, okay? So it's like, it seems like we stop here, we start here, and we look at the maximum value over here, over the precision, okay? We see that, okay, the maximum value is 1, okay? So we say we'll put 1 here. The interpolated one is 1. And then we increase the recall to here, okay? Then we look at the maximum toward this one, okay? We see that the maximum will be something like 0. Let's say 7, okay? And then we do the same. Yeah, it's clear. So we do the same, we look at the maximum, and at the end, you have a different graph that will look like you have the precision, the recall, and you have something smoother. Okay? Not exactly like this, but something smooth. Okay? You compute the interpolation for every query, and then you average among all the queries. So when you fix the threshold at 0, okay, you compute the interpolation for all the queries, and you average them. You plot the value somewhere there. When you fix this threshold, you compute the interpolation for all the queries again. You average and you plot the value, okay? And so on, you have like this movements. That makes sense? Well, so let's get back to the. So you have something like this, and you want using the interpolation, you will end up having this. Okay? So what we expect you here is to implement the 11 points interpolated average. Instructions are there. I have also just clarified them. Okay? So you can create any intermediate function that you want, or that you can reuse it. And then you have to make sure that your code passes all these assets if you want to make sure that you have a good implementation. You also implement the normalized discount cumulative gain. For that, you have this Z, which is the ideal discount cumulative gain, okay? So for this ideal, you use it to normalize for all the queries, okay? And the same, you also have to implement pFound. You have the formula, you have the search result and the relevance, okay? You implement them, you make sure that it passes the tests, okay? And you have the master task. If you want to go for it, I advise you to do at least the first one, okay? So here, what do you have? You have something that is close to the hero world, okay? You have a set of documents which have like document ID, the body and the title, okay? You have a set of queries. The queries can be what is the similarity laws, blah, 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 blah. For this query, we are looking for the document that are relevant for this query. This is what you do in Google, right? You type a text and it finds documents that are relevant for this particular text. And for our data set, we have the relevance matrix, which tells us that this query is relevant for this document. Oh no, this document is relevant for this particular query, okay? Well, so these are stored in different JSON files. So what you want to do is to load them and then make this read crowd field, which will return documents, queries, and relevance, okay? Make sure that you can make use of, all of your matrix functions so that you can pass the right parameters and it return the right values, okay? So you should have something in this format as well. For each query, for each result, what is the ranking, okay? And then you have a very naive search engine, which will take those queries and the documents and return a ranking of those documents. So this basically does what? It just counts the occurrence of each word in the query, in each document, in the title or in the body, okay? And it will sort them by orders of occurrence of the tokens or the values. Very naive, okay? And then you have to evaluate how is this ranker performs on the data set that you have, okay? And you can evaluate it using any metrics that we saw. For example, you print the map, you print the interpolation average, also print the normalized discount cumulative gain, okay? And then you have the beta search engine. So here you are allowed to use something more interesting as ranker. You have the embedding or the transformers, where you can take the tests, given test, and embed them into a space, such that the space will also account for the similarity between words, the semantic of the words, and all these things. Okay. If you can also make use of the connection between words and all these things, you can build a better model. Okay. So here you are allowed to use any embedding that you may use. Okay. To first, one easy way to do it is to map the body of the text to a space, to a vector. Okay. You can also map the query into a vector. Okay. Now you have the query as a vector and the body also as a vector. You can compute the similarity between vectors, right? Because remember, those vectors will also embed the information about how words are close to each other and also the semantic of the query itself. And by doing so, you have a better search engine, right? And you can test it and see how is it robust to some weight input or output. Okay. But at the end, you should also compare this new search engine with the previous one. We saw the metrics that you can use to compare, right? So you can plot the normalized discount cumulative gain score for this search engine and for the previous one. Okay, you have some plotting to show, okay, this model works better than the other one, okay? But sometimes you also want to make sure that the difference is statistically significant, okay? So you do some statistical tests, make sure that, okay, indeed, they are different, okay? So for that, you will use the Kolmogorov-Smirnov test to compare distributions, okay? To see whether one distribution is different from other. If the distribution is different, this means that, okay, your ranking is not returning the same result, okay? And also you can make sure that the difference between your metrics is also statistically significant. There's a link there if you want to recall what is Kolmogorov-Smirnov test. You can read down, and there are also packages that have already implemented in Python. You just will use them, okay? So that will be it for the homework assignments. Again, you are not, it is not mandatory to do the task for M, but feel free to do it for practices to touch more, to have your hands dirty on much more interesting stuff. If you have any question, feel free to write me on Telegram, or if you have any question now, you can go through the text. I'll be here, read it. If you have something that you don't understand, what we expect from you, let me know, okay? Yeah, so read down the description for the time that we still have left.